Hello guys, welcome back to another episode of Talks Riders. In this video, we want to discuss domain decomposition, high performance domain decomposition, which is actually something that completes our previous discussion on parallel computing in the previous video. Let's go for it. So in the previous video, we discussed parallel computing, message passing interface, and all these things. And when it comes to finite element and FreeFEM, the main application is when we want to decompose the domain. So that's where the domain decomposition term comes from. We want to decompose the domain, partition the domain, the computational domain, I mean, and distribute it among available computing nodes. So each node can contribute to the solution and they work all together, and as a result we can have the simulation output faster or in less time, let's say. So similar to previous episodes of the FreeFEM series, I have a couple of examples. Here I have only 3 examples because there are a lot of things to discuss here, and probably in the future we will have a dedicated series on this because this is actually something we talk a lot about in the future in Talks Riders. But I put a link here to the website of my dear friend Pierre, which has really nice examples and tutorials on FreeFEM, mostly on parallel computing in FreeFEM. And most of them are related to domain decomposition. He's also one of the main developers behind the recent advancements in this field in FreeFEM. So you can find a lot of tutorials there, detailed tutorials there. If you're interested in this video, I just want to cover the concepts, the main concepts behind the domain decomposition in FreeFEM and the way that you can use it. Actually, with the work of these developers, it is quite simple to get started with domain decomposition in FreeFEM, but still later on, if you want to go for more advanced things and you want to have control on the solution and the way that the partitioning happens, you probably need to go a little bit more into it. So I start with opening the examples with a text editor and also a terminal on the directory. And so let's start with the first example, which is actually, which tries to demonstrate the concept of partitioning. In this case, we use a tool called METIS, and METIS is actually a tool we use for graph partitioning, and graph partitioning is actually a live and an active line of research, let's say, in the mathematics, applied mathematics. And there are different tools also developed for that. METIS is one of them. ParaMetis is a parallel version of METIS, and Scotch. These are quite famous graph partitioners. We quickly talked about Scotch in the MMG video, if you remember. And in this case, we use METIS directly in FreeFEM because it is actually a plugin. So we load a plugin, METIS plugin, and then we have a mesh. In this case, it is actually just, let's say, a square, and with 2 labels for different parts. So for the upper part and the lower part, although we don't necessarily need it. So this is just because it comes from a simulation. And then we build the mesh. So the mesh is relatively fine. And then we define a finite element space from the type P0 on it. And then we call METIS dual function coming from this plugin on it. So we say that this is actually the parts being called as an array, and then on the TH, which was our mesh, and the number of partitions that we want to have. And then we plot the partitions here, different colors for different partitions or subdomains, let's say. And later on, I will show you how you can assign these subdomains into different CPU cores in order to solve partial differential equations, in order to compute a numerical solution of them in parallel. And later on, down the road here, we have like a kind of visualization just to plot only one of the subdomains and counting the number of nodes in each partition. So this is just for demonstration, for showing you how you can do that if you want to do that really like hard coded into your codes, because later on I will show you that all these things are actually encapsulated in an include file, external code that you can load into your FreeFEM scripts and use them. So in this case, I run a FreeFEM example 1, and I turn off the verbosity. So FreeFEM, this is the mesh, as I told you, the simple square, and then I press M just to show the mesh, and as you can see, these are different partitions that the METIS has created, 32 partitions. And then I press enter because there is no weight, because there was a weight actually here, as you can see. So these are already calculated. I need to press enter, and then it goes to the next plots that are created. And as you can see, these are actually different plots and actually different subdomains, different partitions, and counting the number of partitions, number of elements in each partition. As you can see, they are more or less the same, and that's why this is actually very important. That's why I told you this is an active line of research for different methodologies and stuff, because we want to have more or less the same number of elements in each graph. And this is very important because we want to distribute the load, computational load, into different nodes, available nodes, equally. So that was the first example. In the second example, I want to show you how you can simply create overlapping mesh, which is similar to this partitioning, but for finite element computation, we need to communicate. We need these these partitions to communicate using message passing interface. And for doing that, for imposing properly boundary conditions on each subdomain, because then each subdomain is a single and isolated finite element problem, and we need to impose proper boundary conditions on them. And for doing that, we need some ghost elements, and those ghost elements are coming from overlapping mesh in most of the time in parallel finite element computation world. And for doing that in FreeFEM, it can be easily done using the PETSc plugin and also an include file called macro-DDM. So for in order to show you what that is and what is external code, because we already talked about these IDP files, this is actually a very nice file that encapsulates and hides a lot of complexities of this domain for partitioning stuff in a single file. Then you can just call it and call some functions on it. In this case, for example, this build the mesh to partition the mesh and create overlapping or non-overlapping mesh, which is in some cases also the mesh that you need, and a lot of other operations. And what it needs is only just a plugin of PETSc being loaded, and also a macro showing the dimensions that we have in this case. This is a 2D problem, so 2, and if it is a 3D problem, then it becomes 3. And for this file, in order to see it, I can see where FreeFEM is installed. I just want to quickly show you what a directory, what it does. So in this case, this is where I have installed FreeFEM. So I go to the directory. Here I have this, and I think they're in the shared directory, but I can also use the tree command just to see. Oh, this is too much. So maybe limiting the structure. Still I don't see it. It should be somewhere here. I guess it is here. So L4, just want to see the directory structure. And yeah, these are here. Include their header files for C++ and stuff, but IDP. So if I list lib FreeFEM version and then IDP. So these are the different files that are already there, and this is the file that I told you about. So if I open it in Atom, you can see that it is macro-ddm.idp. So this is the file. As you can see, this is actually an extensive file with over 2,000 lines. And then what it does is actually, as I told you, it encapsulates partitioning and a lot of more operations that are needed for parallel solution of partial differential equations in FreeFEM. So we just call it, and then we use a couple of defined functions in it in our script, and then we are done. As simple as that. So in this case, we have the same mesh, again, same size, but we just call build the mesh on a mesh from this file, and then it automatically becomes an overlapping mesh. And in order to see it better, I want to save it in a VTK file. So we can visualize it with ParaView called out.vtu, and in this case I just pass something called x that contains the coordinates of the mesh, of the elements, because this is P0. We have already discussed all these things in previous videos. So I run this, and now we know, so I go back to the directory where we were, and because this is our, at a PI file, I need to run it with the MPI version of FreeFEM. So I can either run it with MPI run or directly go on FreeFEM MPI. So MPI and then the file name. So example 2, overlapping mesh, turning off verbosity, and we are there. So in this case, because there is no no parallel execution, I have only one file, so I can quickly show you. So this is the out.pvd. I could have opened that directly. So the out.pvd, and it is only one mesh because there is no overlapping, and this is the coordinate x. But when I start to run this, with MPI run, a number of executable, for example, in this case 6, I just want to show you what happens. So I can also remove these 2 files, but that's fine. And then when I run it with 6 CPU cores or 6 MPI nodes, then I have a file here called out_6. And then it is a number of nodes we have, and then I have also 6 other VTU files corresponding to each partition. And I just want to show you how it looks like. So I run ParaView again. I open the file, and in this case, I open the PVD file out6. I press apply, and then you can see here that I have actually 6 partitions. Still the coordinates or the solution here, that actually the entity we have, it is P0 with this icon we can see. It is plotted here, but we have actually some partitions, some subdomains here that I can see by using called, I think, multi-domain explorer or something. So yeah, multi-block inspector. So I right click somewhere or from the view menu and multi-block inspector, and I have it here. And as you can see here, when I select any block, I can have it visualize, or I can, disable all of them, like hide all of them, and starting to have them plotted one by one. And what is really nice here, what is really cool to see, is actually, for example, for the first block, for example, for this one, I have the mesh here, and the neighbor one, the adjacent, let's say, domain, has some nodes shared with this one. And this is actually why we call it overlapping mesh. So as you can see, this mesh, these elements that are actually 3 or 2 in thickness, these are really essential for imposing proper boundary conditions on the subdomains. And this is the way that FreeFEM treats, or let's say solves, partial differential equations in parallel. Late in the next example, I will show you how to do that, but behind the scene, this is the most critical thing to have: an overlapping mesh that has some elements, ghost elements, shared among adjacent partitions. So yeah, this is the way that we can create a partition mesh in FreeFEM. Super easy because thanks to this IDP file. And then in the third example, let me remove all these files that I don't need actually. So VTU and PVD. Yeah. So in example 3, we have like a Poisson equation being solved first in serial. This is a code that we have seen several times in this series. And so it doesn't need any explanation, but I go quickly over it. We have a mesh, which is quite fine in this case because I wanted to take some time. And then I define the var_f formulation. I told you when we were discussing solution of partial differential equations that var_f is the preferred way because we can use it for parallel computing. You cannot use parallel features of FreeFEM with the solve or problem keywords here. So we move everything, we don't need to move everything to the left-hand side. This is variable formulation of Poisson equation, so the weak formulation, and then we have a matrix A that acts as a left-hand side and B as the right-hand side with the degrees of freedom for P1 space, and A and B computed like this. So left-hand side, space P1, and so this is a bilinear term, and this is linear term that can be computed like this, and then we solve the solution. We solve the linear system of equation, and we store the results in the solution. And then I have something here to write the output to a sol.vt file. So I quickly run this file, FreeFEM example 3, Poisson serial, and turn off verbosity. So as you can see, it takes some time because the mesh is quite fine. I run ParaView and solve the VTU, I press apply, and this is the result of the Poisson equation with the boundary condition that we imposed here. So now it's time to see how the parallel version works. I open the parallel file here and let's see them side by side. So as you can see, everything is almost the same except some minor differences. The first one is actually we need to load the PETSc, specifying the dimension before including the macro DDM. This is very important. It should be defined before that because this file uses this, and including the macro DDM file. And then we go on as we went actually here. So mesh defined in the mesh, space P1, also the varef exactly the same, no changes here. And then we have another difference here. Instead of matrix A, we have mat, which is actually the data type that is used by this plugin and this file. And the B is similarly defined, but with the math A, we need to call a function here, create math from this file or plugin, that this is where the overlapping partition is created. So as you can see, we do not need to call build dmesh the way that we did it in example 2. Here, this function automatically calls that. So after this statement, the mesh is overlapped. And this is very important to specify the type of the finite element space that we want to use on this. And there are some more details on this that you can find on other tutorials, or later on, as I told you, we will discuss it in a dedicated series. And this is actually something very interesting. And if there is one reason that we will go for that series, it is because of these details of PETSc. I quickly talked about this in the 9th episode of the FreeFEM series when I discussed different solvers. But this is actually a very beautiful world of theory of computation. And when you can put it into practice, different preconditioner types, different solvers, and what kind of combination of like preconditioner solver is suitable for each type of PDE. So this is really, really cool. And this is where you can easily connect all these parallel computing things to the world of PETSc. And as you can see, this is really easy. You just need to create a matrix and then set parameters. As I showed you before, you can easily modify these things from the command line as well, similar to what we did in the episode 9. And then A and B computed similarly. And now we know, with the things that we discussed in the previous video, we are running this with, parallel computing things and like disciplines and MPI. And this is actually partition mesh. So A and B are computed separately, or let's say individually for each partition. So each CPU core will have its own A and B, and when it solves the solution, it is the same. So each CPU core has its own solution, in this case, computed, and then we can have them saved into like different VTU files, and this is also kind of parallel visualization or post-processing. So this is really cool. This is the way that it works. And now we can just see it in action, that how it runs. But before going for that, I just want to draw your attention once more that there are not so many differences between these two codes. But when you want to use, parallel finite element in FreeFEM, you should also have a little bit of background on parallel computing. So the things that we discussed in the previous video, those are really essential to know here as well. But I don't want to go back to them here, so I just want to show you how it works. And in this case, I run it with MPI run and the MPI version of FreeFEM. Example 3, parallel, and let's see what happens. So in this case, the solution will be also faster. So as you saw, it was quite fast. You know, most of the time was spent on generating the mesh, and for the rest, it was really fast. And now we have like a P6 PVD that we can run, that we can visualize using ParaView. So P6 PVD, which is the parent file that includes all the the parallel or let's say individual submesh or partitions, and these 4 zeros are for the time step. So when we start to do this in, you know, like for time stepping schemes that we had before in TuxWriters, like in the FreeFEM series as well, it becomes really like 1, 2, 3, and then it means that you can have like parallel solution over time. So let's see how it looks like, and I open it. As you can see, these are the mesh partitions, and these are really because of the overlapping mesh, as we discussed in the previous example. And then this is a solution, very nicely computed while we were working in parallel, so really using 6 CPU cores as the computing nodes to calculate the solution of this Poisson equation. So yeah, this is the way that you can do this. This is the way that it can be implemented. And as you can see, this is very easy. But later on, I will provide you with more examples on this from real world applications, let's say, like we start to solve Navier-Stokes equations or reaction diffusion equations in parallel, and then you can see how we can combine the knowledge that you got from this video in addition to the previous video, I mean the episode 10 for parallel computing, and then we can combine all these things together to do really cool stuff. So I hope you enjoy this, and I hope you have fun doing this on your own pace, and see you in next videos. Bye.